Now let's see this figure again.
You keep coming back to this figure.
Yes. So, if you look here, I mean, you have this big structure, of course. Then there is this thin element. I also see some pattern here. It's not very clear, but there is some pattern. It's not just
there
plain sheet.
there
That
is-
much is clear,
exactly. It's not. Yeah,
right?
it's not just the sheet.
Yeah.
Yeah.
It's not obvious what it is.
Yes, but there is some
Yeah.
pattern there.
Yeah. So, see, you were saying here the resistance is low, what you will do, etc. Now, let's say the area available for you to measure is only this much. Let's say this is the space he or she has given. Okay, you can introduce your sensor and measure.
Okay.
And we have said, okay, we are going to make use of, I learned about this strain gauge recently. So I want to make that dimensional change. I mean, pick that dimensional change and get a change in resistance.
Okay.
Will I just put a,
Straight line.
strip like this and then try to measure? Or try to measure from here? Or what shall I do?
I think. I mean, area-wise, your options are limited.
Yeah. You cannot go beyond this.
You might want to make it into something like a coil.
Coil?
Planar,
Uh-huh.
kind of a meandering, like a meander coil or something.
Why?
Or a mesh type of coil.
Why am I doing that?
Because if you want, let's say, a certain length, right? And if that length doesn't fit in that area, you could have the same length by actually having that, let's say, a meander pattern.
So the overall resistance change will increase.
Yes.
It's like the potentiometer that we have made.
Yes.
Instead of having one wire,
Yes.
you said why not wound on a
Bombing and
wind it on a bobbin, and then get more resistance wide.
Yes. So kind of a similar principle, but in this case, the difference is this is planar.
Okay. So what you're saying is come up with some structure like this.
Yes, something like this. Right now, if you lay it out
Yeah.
linearly, it is long.
Long.
So,
And then measure this resistance.
yes. Something like this.
Okay.
It doesn't have to be the exact shape, but the idea is it's this.
I think I have a better picture.
Ah,
So
kind of a rectangular structure.
see, you were saying like this. Something like this.
Something like this, yes.
I can see that shape there.
Yes.
But I see more there. In the sense, you look at these regions. Sorry. Look at these regions.
It looks like some sort of...
They are actually wider
Yes.
than these regions.
There. There.
Manufacturing fault?
I don't think so, because it's too perfect.
Yeah, it's
fault.
right. Looks like it is intentionally made.
Yes. Because they all look the same. It's not in just one or two places, right? What is that?
I'll give a hint. So let's say I'm going to pull this in this direction. I'm going to expand this.
Okay.
So what will happen?
Is one side fixed in this case?
Or let's say I am touching both sides and pulling.
Okay.
I mean, it could be on a material. I have introduced this strain gauge.
Yes.
And then this material is expanded.
Expanded. Okay. From both sides.
Both sides.
Yeah.
Now, there will be increase in resistance for all these portions.
Correct.
All of them are connected in series.
Yes.
Right? Now, let's say the same material also had, we have discussed about this dimension.
Yes.
Let's say it also has dimension change in this direction.
The width.
Okay. If this is also changed
At the same time.
okay, then what would have happened? Resistance of these portions will also increase.
Correct.
Okay. So I don't know which direction there was expansion. Again, kind of selectivity.
Yes.
I wanted to be selective that how much is the delta L by L here? I'm not interested in this. Yes. For example.
Yes.
If so, how will I make these portions less sensitive?
Make it a little thicker.
So you just make those portions thicker
Than the other ones.
So higher, lower resistance.
Yes.
So the relative, the
Change in
compared to total resistance provided, these ones are providing much more resistance compared to these small ones.
Yes.
You also made it thicker. It became negligible.
So this is how you compensate.
This is how we make it, we compensate and kind of make it more sensitive to particular directional.
Longitudinal direction.
Yes.
I see. Yes. And that also explains why you cannot just have this device, as you said, you just drew a rectangle, square, and you just put two,
Yeah, so that will be good for nothing.
Nothing, right? Because it's short and wide.
Yeah, it could change due to this.
Yes.
You will not be able to make out. It will not do the purpose.
Yes.
Or serve the purpose.
But generally, when we are using this kind of strain gauges, do we know what we are trying to measure?
Yes.
We do.
Yeah.
So, because you said, in this case, you're saying it's pulling this way and it's also being pulled this way.
Yeah.
But generally, if you're using this kind of thing for a specific application, do we have an idea of what we are trying to measure?
So, that is, most of the time we know the structure and what kind of deformation it will have.
Yes.
We will have an idea. But there are cases where we don't have an idea. There, I think that solution is coming soon, but anyway, we can explain.
Okay.
So, let's say this is sensitive to X direction, this strain gauge.
Okay.
So, I'm making, strain gauge in this fashion. This became sensitive to X direction.
Yes.
Now, I will put another one 90 degree rotated, which will be sensitive to Y yellow.
Yeah, that's a possibility.
Yes.
So if there's any output from that, then you know
Correct.
that also plays a factor in the result.
Yes. So in the same structure, I can put both of them and measure from them individually. So I allow Rx, that gives me the strain in the X direction, and Ry, that gives a strain in the Y direction.
So you have two separate structures now.
Yes.
Strain gauges.
Yes. If you want to resolve further, you may have to use maybe in 120 degrees, 3 of them.
Yes.
There are structures like that. I have a better picture coming. We will show that also.
So there are separate structures. I remember you said, you said if you're measuring the same thing, then it's better to have it on one structure rather than having three different locations. Constructions.
Yeah, these are some diagrams which I was trying to draw there. This is this sensitive direction, and if you are expanding, the resistance will increase, so it will provide higher resistance. And if there is a contraction, then of course the resistance will reduce. We have discussed this also. So again, this element we are going to attach it to another member which bears the load.
Yes. It's a flexible structure.
Yeah. It's very thin element. Right. Or if I attach it to this, and if this supports that element, that, hey, you don't allow it, I will take care of the load. Then it is not serving the purpose.
No, it's not.
Because our objective is to see the
Yes.
expansion or contraction this element or this structure goes through.
Yes. But then the location where you place the structure depends on the assumption that it's the same all along the structure.
It may not be like that. It comes, it depends on the applications. We'll come to that.
Okay.
So for certain structures, we know from experience and analysis that, okay, these are the locations where you see more strain.
Okay.
So you attach there. And some structures, some places the strain may increase, some places strain may decrease, and so on. So we consider those factors while
Later on.
installing. Correct. Now, see, these kind of elements, they are also, what shall we say, environmental factors. It should not affect.
Yes.
Suppose rain or some moisture comes in, it keeps wrong reading, it's a problem. So usually these are protected properly. As you see here, there is an environmental protection. It will be some kind of a material that saves
the foil.
Yeah. It will be actually filled. Yeah. It may look like a glue kind of thing for us.
Right.
It's so that saves us from environmental factors. It's an environmental barrier, and the strain gauge, connecting wires, and so on. I think we not go through in so much in detail.
Yeah.
But what we are saying is there is a structure to which we attach, and then we protect it, so that it can be safely used.
So can we say this is something like a flexible PCB structure with
it will look
some
like
protective?
It will look like a flexible PCB. I don't know how many of students have seen flexible PCB. Yeah,
but the idea is you somehow write this structure onto a flexible substrate.
Yeah, substrate. Yes,
and then you cover it with something.
Yes,
so it's protected from the environment.
Yes, and there are some specific adhesive that can be used to attach it to the
substrate.
In this case, if you want to attach it to this, you need some
specific adhesive.
Yes, because the adhesive has to correctly pass. The strain information to this.
Yes, and the coupling should be very good.
Yeah, that mechanical coupling. Yes, very good. But these are all very standardized. The strain gauge, as you have seen,
8 interlink.
Yeah, so
it's 56.
Yeah, but it's a widely used, very reliable approach to measure strain.
Boby, I have a question.
You like the strain gauge?
Yeah, I do. I think it's simple.
Yeah,
but it's amazing that it can measure different things.
Yes.
But I do have a question because you talked about the gauge factor, right? And for conductors, it's 2.
2.
1 point something to 2.6 I saw.
Yes.
That's very small, right? So that resistance change can be very, very small if you have 300 something, ohm resistor.
Yeah.
300 something plus point.
Yeah. For a small amount of strain, maybe 350 becomes 350.1.
Yeah.
350.2 possible.
Yes, which is very small. So how can you measure such a small change?
I use a meter and measure. You're not happy?
I don't think a meter would be able to measure such small.
Some resistance measuring it.
So very expensive one.
If I'll apply a voltage and measure the current, then somehow.
I don't think you will see that. No, I don't think so. I think it will not be seen in an output. If you
will those meters will have
in some other
more error,
right? Exactly, right? So there's, even if you connect it oscilloscope or something.
So what you are saying is I have a resistive element like this that changes its resistance,
Yes.
with respect to strain.
Yes.
So maybe before applying strain or before applying stress, it's let's say R naught is the value.
Yes.
And we have seen that it's changing linearly because we are operating in the
Yes. The linear region.
in the elastic region,
Yes.
and then there's a fixed slope.
Yes.
So with respect to strain, it's going to increase or decrease depending on the whether the strain is increasing or decreasing.
Yes.
So I can maybe write it as some R naught into 1 plus x or kx.
Okay.
X is the quantity that you are measuring.
Yes.
X and R naught are related using some factor.
Okay.
I'm trying to generalize.
Mhm.
So what you're saying is, if I write like this, I have R naught plus R naught kx.
Yes.
And it can be plus or minus depending on the direction of x.
True.
This R naught kx is going to be a small value. What are you going to do?
Yeah, I'm
That's
saying
the
it.
question.
Yeah, exactly.
So now my answer is somehow if you can get this change alone as the output.
Yes.
Because your problem was this large resistance, let's say 1000 ohm, then there is 0.1 ohm change.
Yes. So if you multiply or something.
Yeah, instead of measuring that, I mean, the huge amount of it is not changing.
Yes.
So it's just fixed value.
Yes.
So if that change alone can be picked up, you are happy.
Yes. If you can minus, for example, somehow that, and then you can get just that change in resistance due to some strain.
Yeah, nice idea, but I don't know how to do it. What if I have another R naught and I then try to compare with that?
You mean, and you get some
Yeah,
differential
or something like that. So what I have is this. I have this, let's say, strain gauge, which is changing R naught into 1 plus or minus kx.
Yes.
Then what I'm saying is I get another strain gauge.
Yes.
Or a resistor which is equal to the same value.
Okay.
R naught. Can I do something?
And that's not exposed to
That's not exposed to strain. Yeah.
And then
how this, but can I do something with that? It's a question.
Sure, why not? And then if you go, R01 plus kx minus R0, shouldn't you not get?
Yeah, but then again, I should not measure R naught and then R naught into 1 plus or minus kx separately and then subtract.
Yes. Not separate.
Again,
No.
correct?
Yes.
Yeah.
But I mean, what I'm trying to get at is the idea of somehow having something like that. Then in the end, using that to subtract.
Correct. Yeah. So maybe if we send constant current through both of them and then somehow, as you said, measure this difference in voltage, you may get that difference.
But they should not be two different
Not be
systems.
that complicated.
Yes.
So let's try, maybe I will join this and connect this to ground. At least one portion is okay. Let's say this is homology. Yeah. Now, we would like to give some excitation to this.
Yes.
Some DC or AC voltage.
Yes.
If I directly give, I cannot, there will be no difference. I have to measure the current then.
Yes.
What shall I do? I have more of this R naught available. Maybe we can try to play. So let's say I introduce one R naught here, another R naught here, and close this.
Okay.
And then I will apply
Some voltage?
Yeah, some voltage. Now you know.
Okay, I see what.
This students might have solved a lot.
Right. Yes, I see
Let's
what
say
you're
there is a voltage Vs which is applied.
supply.
For now, let's say it's a DC voltage. So here I will have Vs by 2. Here also we will have Vs by 2 when Kx is 0.
Yes.
So suppose if we are measuring the difference,
The difference then should only be due to
should be a function of
Kx. Yes. Because that's the only resistance that
Yeah.
change. Yeah.
So somehow what we were trying to do is seems to be
Yes.
achievable.
Yes. Yes. That's a much better way than subtracting it.
Yeah, because you are able to pick that difference value.
Yes. Yes.
Let's see what we will get if we try to write an expression for V naught.
Okay.
So V naught will be the voltage here, which is Vs by R naught plus R naught into 1 plus or minus Kx
Yes.
into 1 plus or minus Kx.
Yes.
This is the voltage at this point.
Yes.
Minus the voltage at the other side, which is just Vs by 2.
Because R is 0 equal.
Correct, yes. Now all these R nodes are getting cancelled. Correct.
Yes.
So we can take maybe Vs outside. So I have 1 plus or minus Kx divided by 1 plus or minus Kx minus 1 by 2.
Yes.
This is Vs into 2 plus or minus 2 Kx minus 1 minus or plus Kx. Am I complicating? Looks like. Let's see.
Maybe the denominator, no?
Yeah.
Complicated. 2 times 1 plus or minus K.
So it's 2 plus or minus Kx into 2.
Yes.
Something I think it will get cancelled. So I see this 2 and these are going away. 1 minus or plus Kx and this will go away.
So yeah, that's Kx over 2 and 2 is
So
okay. Some is
maybe I can take this 2 outside. This 2 I can take outside. So this will become plus or minus
Kx
divided by 1 plus or minus, 2 plus or minus Kx. Not really nice. I wanted to further refine. Let's say Vs by, we will take this 2 also outside.
Okay.
Then it will become Vs by 4 into, this will become 1 so minus
X over 2.
Kx by 2.
Yes.
Correct?
Yes.
So what he sees, the final output V naught, there is a factor which is directly proportional to K.
Yes.
That we like.
Yes.
I mean, initially, if you are just measuring total resistance, it would have been R naught plus R naught Kx.
That's it.
That's that huge R naught. So some offset there. Now you remove.
Is that that could get
Yes.
ground in that?
Yes. So it's like a Himalaya, and then you are making small changes there, and you want to measure that. So you are happy with that.
Yes.
But one small issue is you have a Kx by 2 in the denominator also.
Yes.
So, but one thing is it's 1 plus Kx by 2. So for small values of Kx, you could maybe neglect that. I mean, if Kx by 2 is very small compared to 1,
Then it's plus or minus Kx.
yeah, then it is Vs by 4 into plus or minus Kx, you get a linear output.
Yes. But
But if Kx is somewhat
large,
relatively, yeah, if it is not negligible compared to 1, then this term will contribute some non-linearity because this is the denominator.
Yes, which is what we saw.
Yes.
In the
So it will
introductive
not be a
lecture.
straight line, it will introduce a non-linear.
Yeah.
So now we know how certain systems can introduce non-linearity into the
Yes. Yes.
Yeah, so this could be a way to measure. And of course, if you measure V naught, you may be mathematically able to calculate Kx. But this non-linearity is a problem. For small values of Kx, of course, I can use. Or if you're okay with that non-linearity, it's fine. Now the question is, can I do something to improvise this? I don't want this non-linearity.
That means you need to get rid of the Kx over 2? Is that what
But
you're
I
saying?
want the Kx. Kx is what we want to measure. I don't want that Kx in the denominator. Of course, I mean, this bridge, I think this bridge circuit students have learned earlier, not for the purpose of measurement or sensing, but as a circuit problem, they might have solved this.
Okay.
So the bridge, this is a Wheatstone bridge.
Yes. It's a quarter.
Yeah, Wheatstone bridge. You have only one sensing element in this, so it's also known as a quarter bridge.
Yes.
And actually, this Vs by 4 shows that, in the sense 1/4.
1/4, yes. Correct.
In case you have resistive elements in all the arms, and here you have 1 plus or minus Kx. In case I can get 1 minus or plus Kx.
Yeah.
And here 1 minus or plus Kx. And here 1 plus or minus Kx. Suppose if you can get like this,
Okay.
then the sensitivity may increase. Because
Okay.
you have, when this bridge output arm goes up, this is going to go down, and vice versa. We will derive this later.
But then if the resistors, all the resistors are exposed to the same strain,
Yeah.
then
You may not be able to get that.
get them.
I'm just getting greedy to increase the sensitivity. But in certain applications, this may be possible. We'll see that soon.
Unless they're in different places.
Yeah. So this is actually feasible, but we will see that.
What if you have 2?
Yeah, if you have just 2 and in opposite direction, yes, I can introduce that here. Yeah, we will see those factors later.
Okay.
But even with just one sensing element, can I get a linear output? Of course, bridge is not a solution then. Maybe we are free to use electronics.
Okay. So we are not looking at the bridge option now.
Yeah.
You're saying there's maybe another way to get a linear output and somehow a large enough signal.
Correct. What we have is this resistive element. I've drawn it in a funny fashion anyway, with some angle. So I have this, which is changing. Sorry. Rx equal to R naught into 1 plus or minus Kx. I would like to get output as some constant into Kx. Yes. That's what I want. Not in the denominator. No. So how will I get? See, I think students have learned this maybe op-amps. I think they have studied. Okay. So let's say we have this maybe if they have studied inverting type, non-inverting amplifier, etc. Let's try one by one. Give something, right? So yeah, let's say I have a inverting amplifier. I connect it in this way. This is connected to the bridge voltage. Let's say this is R naught. Okay. So I have voltage here is 0, or for this they may know the expression directly. It will be minus Vs into Rx by R naught. So it is R naught into 1 plus Kx by R. So which will give minus Vs into 1 plus or minus Kx. Still that 1 is there.
But it's constant. It's there all the time.
But it's there. Which is actually the R naught.
Yes.
Because it got
the initial.
Yeah. So I'm not happy. What shall I do? So is there a way I can remove that 1? So basically somehow I need to have a plus Vs. Correct?
Yes. And then, okay.
Because it's Vs into 1 plus or minus Kx. So that is minus Vs minus or plus Kx plus Vs. So if that is achievable, then one will go away.
Yes.
How to do that? This leg is anyway hanging here.
0.
I mean, we are connected to ground. Okay. Instead of connecting it to ground, maybe we'll give, suppose if I give Vs there, what will I get? This will be a non-inverting configuration.
No. Yes.
So that will become Vs into 1 plus this by this.
If you connect Vs to the
Yeah. That's also leading to something else. What if I give Vs by 2? We'll try that.
So you're adding another resistor now.
We are adding another resistive network to get Vs by 2 here. So this will give an output of this plus, because I have not changed anything for this portion. No. So that will be there. I just need to find out the contribution due to this. So this will be Vs by 2 into 1 plus R naught into 1 plus or minus Kx by R naught. Correct? Yes, so 1 plus R2 by R1. Yes, yes. Let's see what we will get. So minus Vs into 1 plus or minus Kx plus Vs into 1 by 2 plus 1 by 2 into 1 plus or minus Kx. Not readable there. I'll read it quite properly. So, am I making some mistake? No, it's okay. So, this means this is 1 plus, this is plus 1, this is minus. Yes, they will go in.
But you still have half.
Yeah, so this is plus or minus Kx.
Your Kx there.
By 2. I have minus or plus Kx.
So you're still left with a half there.
That's true. So what I'll get is minus Vs into or minus or plus Kx by 2. Yes.
Are you happy with that?
I am happy in the sense it's linear.
Yes.
Also, output is directly proportional to
yes.
Yes.
You're just having it.
Yeah. So I'm happy on those aspects. Now, if you want more amplification or more change in output, either you can increase Vs, that will have some losses in this, or you can have one more amplifier.
No, I'm trying. Connect to that.
Yeah.
And then you get rid of the 2.
Yeah, if you want to.
Yes. But it's linear now.
Yeah.
That was the main objective.
Correct. I mean, 2 objectives were there. I mean, one objective we already achieved by
the bridge.
using that bridge.
Yeah.
We were able to remove that constant term. Now, we have retained that. And in the bridge circuit, there was an issue. There was a plus or minus Kx by 2 term in the denominator.
Yes.
Now the denominator is clean, it's just 2. So which means you could introduce electronics and get better performance.
Yes.
That non-linearity is systematically removed now.
Yes. This is true.
Yes.
Yeah. So it'd be, I guess, easier for us to interpret the results.
Yes. Now
it's linear.
Yeah. So for the user, it will be easier because non-linearity is almost not there.
Yes.
The non-linearity which was introduced by the bridges.
Yes. But when you introduce these electronic circuits, would that add any
of course, there is a cost.
noise or
Yeah.
something like that.
I mean,
or cost.
you have an op-amp there now. It needs to be powered. Earlier, it was just excitation alone. So this op-amp needs plus or minus power supply.
Mhm.
This has to be provided. Of course, there's a little bit of cost. There will be some noise introduced by this op-amp. So that may affect the resolution a bit.
Right.
All these factors will be there. Right.
But it's linear.
Yeah. So now depending on the application, if I want, this is the amount of noise that is allowed, then I can go for an op-amp that assures that kind of.
It's within that tolerance limit.
Yes.